Hello, I'm going to present the Orchestration Analysis and Research Database, or ORCHARD, or ORCHARD. I will discuss the theoretical underpinnings behind an orchestration analysis taxonomy based on perceptual grouping principles that operate in orchestration practice. I'll also present an approach to using this taxonomy for targeted orchestration analysis, for the development of a database with the results of the analyses conducted by a team of composers and music theorists, and some new conceptions and implementations that are being integrated into a new data model, as well as new software for score annotations. Many orchestration names are implicitly related to auditory grouping principles. They organize the acoustic environment and determine what sounds are grouped together into musical events in concurrent grouping, whether these events are connected into musical streams or layers in sequential grouping, and how listeners chunk event streams into musical units such as motifs, phrases, themes, or sections. Perceptual qualities are computed on the results of grouping processes related to the orchestral effects. Focusing on timbre, timbre emerges from the perceptual fusion of acoustical components into a single auditory event. Timbral similarity is involved in auditory stream integration, and timbral differences provoke the segregation of events into different streams or orchestral layers. Timbre is also involved with segmental grouping. Discontinuities promote chunking of musical units, whereas a succession of unchanging or gradually changing blended or integrated instrumental sounds creates a sense of continuity, which would be chunked as one unit. Let's examine the analysis taxonomy with each grouping process. So for concurrent grouping, perceptual fusion results in the formation of auditory events. Event formation depends on concurrent grouping principles such as the synchrony of onsets and offsets, the harmonicity of concurrent sounds, and the parallelism of changes in pitch and dynamics. But the fusion of multiple sound sources in orchestral blends also depends on spectral relations, in particular spectral overlap of concurrent sounds and overall spectral density. Given that concurrent grouping precedes the extraction of auditory attributes, timbre perception depends on concurrent grouping and can be manipulated in orchestration. This is the current revised version of the taxonomy. In the concurrent grouping, we distinguish blend from non-blend. In blend, we have timbral augmentation, where a dominating instrument is augmented by one or more instruments which may not be identifiable, and timbral emergence, where the identities of the constituents are subsumed into the whole. This is a concept that was developed by Greg Sandell back in the 90s. Non-blend is the general rule when different sound sources are simultaneously present. The specific case of timbral heterogeneity here refers to cases in which synchrony, harmonicity, and parallelism exist, but the spectral properties impede blend. These effects may either be sustained over time or occur briefly as a punctuation. For sustained events, they may either be stable in terms of instrumentation, or the instrumentation may evolve over time. Here is an octave doubling of English horn and muted trumpet, from which emerges a kind of new reedy sound, sometimes referred to as a foghorn-like sound, that remains stable in character. This is from Debussy's La Mer in the first movement. Most of the examples I will play are created in the orchestral simulation platform IRCAM by Félix Baril and Denis Boulian, and are part of the OrcPlay music library. Since they are realized as multi-track sound files, one can select individual tracks or combinations of tracks to play in isolation from the rest of the musical context. Now let's look at sequential grouping. Auditory streams mentally represent the behavior of sound sources over time, and perceptual organization connects similar sounds into auditory streams on the basis of continuities in pitch, timbre, loudness, and spatial position. Successive sounds from the same source tend to be more similar in all these parameters, including timbre. Sounds with different timbres tend to come from different sources. Therefore, composers can use timbral differentiation to create the segregation of streams or of orchestral layers or strata. And they can use timbral similarity to promote integration and coherence within these musical structures. Timbre-based stream segregation is directly related to timbral dissimilarity, so we can use timbre spaces to predict the probability of timbre-based stream segregation. So we have integration of event sequences into streams or surface textures, and segregation into streams or orchestral layers. Surface textures are situations where it can be heard that more than one sound source is present, but they are difficult to separate perceptually and track over time. This often occurs with interleaving musical material in two or more instruments. Orchestral strata are layers distinguished by their salience into foreground, background, and sometimes middle ground layers. As before, these can be either stable or transforming in terms of the constituent instruments. In the example from Vaughan Williams' Eighth Symphony, we note that the registral and rhythmic differences, particularly the fact that one stream is in 6/8 and the other in 2/4, between the two groups of blended instruments are enhanced by differences in timbral brightness. First, let's listen to the homophonic blend of clarinets, bassoon, horns, and trumpets. Then the higher pitched stream of blended flutes, oboes, and bassoon in unison and octave doublings. And then both together in the full musical context. Note the overlapping pitch registers, and yet you can still hear clearly these two streams independently of one another. Now let's look at segmental grouping. Any kind of acoustic discontinuity can provoke segmentation, including timbral discontinuity. Changes in timbre cause segmentation or chunking of sequences into small-scale groups. Large-scale sections in music are often formed on the basis of similarities in register, texture, and instrumentation within a section and discontinuities at section boundaries. So timbre change can contribute to boundary creation at a number of hierarchical levels from local to global, and timbral similarity contributes to the perceptual coherence of events within these segmented units. There are several subcategories of timbral contrast, such as the antiphonal contrasts alternating between instrumental choirs, the echoing of a pattern in one instrument by another that simulates distance through the timbral change, the shifting of a musical pattern from instrument to instrument in a chain, general local contrasts that don't conform to these three, and then larger scale sectional contrasts. There's a play between continuity and discontinuity in real music, and this has an effect on perceived boundary strength and segmentation. As an example of this, there's a general timbral contrast can be used to set off different musical materials with distinct orchestrations in order to highlight the contrast. Here, local contrast and instrumental groups are used to set off the alternating musical materials in this piece from Sibelius' Second Symphony. The first group will remain fairly constant with strings and horns, although the horns drop out in the last instance. But the second group changes over time from cello to cello plus bassoon plus timpani to cello plus contrabass. And then it changes over to high woodwinds. Modeling Modeling concatenated contrasts involves simply detecting changes in instrumentation. However, the Sibelius case is more complex as the groups are elided with overlapping entries and exits, which poses problems for computer modeling of these kinds of effects. Here's the full analysis taxonomy. So we have a kind of hierarchical structure in which events are formed that then get connected into sequences of streams, textures, and strata, which in turn get segmented at various hierarchical levels into musical units. However, my hunch is that these levels of grouping feed back upon each other in complex ways, and some of the modeling work we are doing now with Aurélien Antoine and Philippe de Paul is raising this issue. So now let's look at applying this to analysis. Our original approach was exceedingly time-consuming, with about a third of the time devoted to analysis and two-thirds to manual data entry. And I'll talk more about technological solutions to this in a moment. It involved a team of annotators, which were composers, music theorists, and musicologists who worked in pairs. Individually, each person examined the score and listened to recordings, and listening was important because we're interested in perception and just not gazing at scores. They had to identify salient examples of these various orchestral devices in the taxonomy, annotate on a PDF version of the score what they found, so they would box passages using a color scheme that identified the orchestral device in question, and they were to keep a journal of issues arising in decision-making processes. Finally, they would upload all the files to a server. Then they got together in pairs and compared their analyses and developed a joint analysis by consensus. They were to catalog the details. At first, in our first round, it was in spreadsheets, Excel spreadsheets, and then in a second round in Google Forms. And this will eventually change to an orchestration analysis platform that I'll talk about in a moment. And they had to keep a journal of the various divergences and solutions they came up with and applied all the new files to a server. Then we would have group meetings where the analyses would be shared and discussed and issues raised, and then we would refine the analysis categories. There was some evolution of the analysis taxonomy prior to the creation of the first instantiation of Orchard, and then a major reconceptualizing of the taxonomy, which is currently being implemented in a new data model. Finally, we had to rotate the partnerships to avoid developing idiosyncratic analyses within teams. And then there was a verification stage where a new team of annotators repeated the procedure with movements that were previously analyzed by other teams. They also had to look at the various concordances and divergences and log those and code to find themes and patterns. Basically, this led to definitions and rules that needed to be modified for consistency to help the whole taxonomy evolve and become more consistent. And finally, there's an editing and review stage, which basically found that some of the analyses were sufficiently reliable, and those got uploaded to Orchard, and some actually need to be reanalyzed. Now, in the old school form, basically, the annotation consists of a span of measures, a start and an ending time of the recording, the type of orchestral device in the taxonomy, which instruments are involved, and a strength rating where people had to say how strong this particular effect was in that particular recording. And they could have various kinds of free text and notes and so on. At the beginning, they were entered by hand into Excel spreadsheets, but then afterwards we developed a Google form to make some more consistency. But still, like I said, this made the annotation part very, very time-consuming, because 1/3 was for analysis and 2/3 for manual data entry. The result was that we have about 4,300 annotations in 67 movements from composers primarily in the classical and romantic periods up to the early 20th century with Vaughan Williams, and then one wind band piece by Kelly from the 20th century, but which uses normative orchestration. The design of Orchard involves a number of different elements. PostgreSQL is an object relational database system that extends the SQL language by adding many features. It has a strong reputation for its reliability and data integrity. Solr is a search engine that provides search capabilities through HTTP requests. Although it provides powerful features such as full-text search and faceting, we are currently switching to Elasticsearch due to its scalability. As this project grows, more data will be available to query, and Elasticsearch will automatically reorganize these clusters of data, thereby improving the search speed of the engine. This change will also allow us to accommodate data mining and machine learning in the future. We developed the Orchard web-based interface using Django, a high-level web framework in Python. Its architecture allows us to easily set up websites by automating many tedious processes such as writing the boilerplate code, linking API endpoints with our model, and so on. Furthermore, Docker lets us separate different aspects of our application into several containers, which are mini virtual machines. These containers will each run on their own individual isolated virtual environment so that they will not interfere with one another. The kinds of functionalities for the user that we set up in here, who are actually using this to explore the different annotations, are simple and complex queries, You can view annotated scores and stream the musical clips for the annotation in question. We can upload future analyses and integrate them into the collection. And through the queries, there's various kinds of sorting and filtering of the results that are possible. Finally, we've recently integrated the possibility to save queries to a user profile for each user so they can come back and check queries that they've had before in the past. Here's an example of the query builder, okay, so that a user can browse the analyses and conduct a simple search through keywords, but also create complex queries with the query builder. It lets us specify the parameters in a hierarchical format. It sort of looks complex, but if you understand Boolean operators, it's really quite powerful. Here we're looking for a stratification effect, okay, that has progressive changes and has instrumentation, the violin in the foreground layer of the stratification. Also, it's by composers whose names start with either MAH or MUS, and the effect has to have a strength of 3 or more on a scale of 5, as annotated by the annotators. When the query is submitted, down here, submit, a list of annotations appears, and they can be sorted hierarchically by various criteria, such as composer and strength here in this particular case. And they can be saved in the user's profile. When the user clicks on a given query, okay, so if I get one result of the query, I can click on one. Then you basically get a page that has the score at the page where the annotation in question exists, and a sound clip of just that part of the music where that annotation exists, okay. One of the difficult things here is all the annotations are superimposed on one another, so we'll see how that can be evolved. Now here we have the annotated score and various data concerning the effect in question, as well as the clip. So we have all kinds of information about which instruments were involved, what was the nature of the effect, what was the time in the score, in the recording, the pages in the score, the measure numbers, and so on. Now to get away from manual data entry, we've been developing a computer-based score annotation platform with Félix Barri and Beatrice. In OrcView, scores in PDF or music XML format can be annotated. One can select different types of grooving effects, which each have their own color. The different annotation tools correspond to the analysis taxonomy, the new analysis taxonomy. Each annotation is labeled for future reference in refining or sharing analyses. Bars and staves are already specified in music XML files. But for PDF files, the program attempts to recognize bar lines and staves, and these can be corrected by hand. Furthermore, time tags can be entered for each bar so that the corresponding recording can be played at the appropriate moment when a given annotation is selected. Most importantly, the results will be exportable directly to Orchard, where a script will translate the music XML code into the necessary structure for the data model. Future taxonomies that are under development or slated for future development include orchestration techniques and Lasse Thoresson's oral sonology. One of the advantages of OrcView as a visual interface is that one can selectively display the various effects. So for example, from the full annotation on the previous slide, here are just the various blends in concurrent grouping. Here are the segregated streams, and here are the segmentations. Eventually, OrcView can be used as an interface to Orchard so that just the annotation being examined is shown on the screen. So that's about it for the presentation of Orchard. I want to thank the whole Orchard team, conceived by Meghan Goodchild, Kit Soden, and myself, with an initial implementation by Alistair Russell, followed up by Bea Lopez, and then the new implementation team here with Michael Lee, Alfa Barri, Tong Lee, and of course, trying to relate everything to OrcView with Félix Barri. And I'd like to acknowledge our sources, particularly the Actor Project, Orc Play Music Library, and then our various funding bodies. Thank you very much.